Welcome to ECE 3270, Introduction to PLC Programming, Lecture 7. Today we're going to be talking about the importance of comments and structure in PLC code. And this is sort of, I guess, a little bit transcendental in that it applies to most code, not just PLC ladder logic. So we're going to be discussing the importance of structure and comments. And then we're also going to talk about the expectation and requirements moving forward in the lab. So everything after this lecture, you need to code to the requirements outlined here as far as how to comment and structure the code. That being said, we're also going to look at a short example to see what that looks like in actual ladder logic. But first, let's have a short industry connections video. Today we're going to be talking about robotics. So we've introduced two types of motion so far. One was pneumatic cylinder-driven motion. The second type of motion was linear motion controlled by a linear servo or a linear stepper motor. So in this video, we're going to see an exhibition of a robot being used to supply motion. So robots have different configurations, and that's a broad term. A robot can be something as simple as a three-axis, what's known as a gantry, a three-axis gantry system. That means it's not able to rotate, but it is able to move in X, Y, and Z. It can be as simple as that, or it can be as complicated as you want it to be. So even up to, I've seen seven-axis collaborative robots that are intended for interaction between human and machine. So robot is a broad term that typically means you have some sort of combination of degrees of freedom, and you have servos that are driving each of those degrees of freedom. And that, in general, is what is meant when someone refers to a robot in the industrial world. So let's take a quick look at this video. So first, we're going to see, this is the interior of the robot cell, and I am perched above. So here we see a valve manifold on the side of the robot arm that is going to control the motions at the end effector. That's what we refer to, or how we refer to the manipulator of the robot, the thing that actually interacts with the different pieces, the end effector. So that valve manifold here is used to control this end effector. So it comes over and it takes a picture and realizes it doesn't have the right tool to be able to pick up this part. So it sets down that tool, picks up a different tool. And it's using pneumatics to open and close those grippers and to pick up that head. Drops off some parts at the pallet. And now it's searching. It's searching for one of these parts, but it's doing a grid search. And see, it's taking a picture with that camera. So robots, that's an odd pronunciation. Robots come into play when the motion needed is somewhat unpredictable or just highly complex. So in this case, it was both, right? It's hard to predict exactly what's going to be necessary to accomplish this function, and the motion that was necessary was highly complex. This video is a little bit loud. So now it had to go and change heads to be able to pick up this part that it found, and it used the camera to know exactly where it was at. So notice how precise this is. So there are small pins here that have to precisely line up with these components. turn the audio down. So there are small pins on these parts that have to precisely line up with the tooling over there on that dial. And so this camera helps to precisely locate these components, and so that way the pick is very precise and the place can likewise be very precise. It hasn't found one it liked. Still looking. Like that one. So here we're seeing the robot being driven by a camera. So we have vision being used in industrial situations. We have a robot being used to provide complex motion, and we see that it's still fundamentally making use of this pneumatic control. And then it's waiting for a process to finish, and when this comes around, this component will also be loaded to this pallet. There we have it. So most motion that you'll see in an industrial machine, in industrial controls, is pneumatic-driven motion. That's what we see on this machine here. We see all of the motion being driven pneumatically, and when it's not pneumatic motion, typically that's because you need to have many positions that you're going to, not just one or two, or you need precise positioning, in which case you might use a linear servo. Then there are situations where the motion that you need is not easily defined, or you know it's going to be exceptionally complex, like the motion that would be necessary to take a component from an unspecified location on the cart that was over here in this corner. So those were not held in place. So this robot had to use a camera to figure out exactly where it was, to know where to put this tooltip and pick that component up. So there was no way to know ahead of time exactly where this robot was going to need to go. So it'd been very hard to have used some sort of motion that was predefined and locked in to a certain path. So instead, you can use a robot, and that gives you a lot of latitude to be able to figure out what you need to do. So robots are helpful when the motion that is necessary is not easily definable beforehand, or when the motion is going to be necessarily complex and dynamic. Now, one thing that didn't get mentioned, but should have been obvious, is that to be able to accommodate such a rich and complex function like we just saw with that robot, there's going to be a rich and complex set of PLC code that's running everything. And when things get very rich and complex, they also get complicated. So this complicated PLC code could easily become unmaintainable. And when I say unmaintainable, what I mean is there's someone that's going to have to make sure that machine's running day and night. And when it breaks, it's their responsibility to fix it. And when it doesn't work like they want it to, they have to adjust that. That's the process of maintaining the code. And all code has to be maintained. You know, for instance, the Windows operating system, it always has new updates, right? That is the Microsoft coding team maintaining and extending that code. Same thing with Apple. Same thing with any other code that's written. It doesn't get written once and stay as it has been written. It continues to be maintained. To be able to have code that is maintainable, you can't just simply code however you feel in the moment. You know, you can't shoot from the hip. You're going to need structure, and you're going to need some way of conveying what the code is supposed to do. because you might write something that works great, but maybe it's hard to decipher exactly what's happening by looking at it. This is where comments and structure come in. So it's important to have comments and it's important to have structure for two reasons. Comments lend readability. Comments help make things readable. And structure makes things logical. So we want things to be readable and have a logical order. And why do we care about this? Because if we write code that is not readable and does not have a logical order, then it's not going to be maintainable. And if it's not maintainable, then it's not worth anything to anyone, and no one's going to pay you for it. And ultimately, if you write code that is not readable and not logical, so you don't use any comments, no comments, plus no structure, and this is really important. This is exactly why you should care about comments and structure. No comments plus no structure equals no job. Very simple. It's a very simple relationship. That's why we care about comments and structure. Because if you don't have comments, you don't have structure, then you don't have readable code, you don't have logical code, and that means you don't have maintainable code. And that means that anyone who you write code for is ultimately going to be unpleased. And that means ultimately you're not going to have a job writing code. So there's a different relationship to also bring up. We said no comments plus no structure equals no job. Here's a very good relationship as well. Readable plus logical equals maintainable. So if we use comments to explain what our code is doing, that helps to make it readable. And if we use a good structure, this gives logical order. And that lends itself to maintainability. So readable and logical code is maintainable code. And that's code that will get repeat customers. That's code that will get you promotions, and that's code that will ensure that you have a good career in programming, whether it be PLCs or as a member of a software development team for Microsoft. Either way, if you do not write maintainable code, you will lose your job. If you write readable, logical code that is maintainable, you will excel, most likely. So, to be able to write readable code, we need comments. And in ladder logic, that comes through as rung comments. So we can put comments on a specific rung. So rung comments is how we would go about commenting our code. But there's other things that we can do as well. Tag naming. So using appropriate tag names lends a lot to readability. If you name a tag December, just because you were at a loss for things to call the various tags you needed in your program, but in reality what it's doing is taking in a number from the HMI and then doubling it to display it back on the HMI. December is a wholly inappropriate name. It makes no sense. So using logical and helpful tag names. So keep tag names logical and helpful. This is a requirement. So as you begin to create your own tags and as you begin to add rungs, your code should be commented, and we'll talk more about exactly how much commenting is necessary, and too much is actually a problem. And it's a requirement that you give appropriate logical helpful tag names. So that's how you make code readable. There's other things too, like little decisions regarding how do you go about performing some function. Sometimes there's a transparent or a way of going about something that conveys exactly what your intentions are, and there's another way that may be more clever but not quite as transparent. Typically it's better to go with the one that's more transparent unless there's a good reason not to. So that's not something we're going to major on. These are things we're majoring on. You have to use rung comments. You have to use appropriate logical helpful tag names. Now let's talk more about this idea of logical structure. So logical structure would mean that rungs are grouped into sections that have a similar effect. So what I mean here is, let's say that you have one group of rungs that all work together to take the average of the last 5 things that have been typed into the HMI. Well, then that group of rungs should have one comment to tell what it does, and then those rungs should be together without any interruption, and then there should be a comment that shows the end of that section of rungs. So rung grouping is what we're talking about when I say logical. Of course, code needs to be logical in that it works, but I'm talking about the logical structure of code. So make sure that the grouping of rungs is logical. It makes sense. There's a reasoning behind it, and you're consistent in how you go about it. So it is reasoned and consistent. And this will make your code maintainable. Is it super important to have maintainability in this class? A little bit, yeah, because you're going to have 2-part labs that you need to be able to pick back up where you left off. And in those situations, you need to be able to understand what you have done and what your intentions were, and you may forget in a week. So you need to write maintainable code by using comments, appropriate tag names, and reasoned and consistent logical rung groupings. That also make your code maintainable, and it will put you in good practice for the future if you ever continue in PLC programming. Now let's shift our attention from talking about comments and structure in the ethereal or in the theoretical, and let's talk about it in the very specific. So this is a zoomed out view of the bit latch sequence example that I did to show SOS on the HMI screen a couple of lectures ago. So this is that exact same sequence, and I've just zoomed out the ladder editor so that we could see the whole thing. So notice the structure and the commenting. So first of all, I have a comment up here that just says sequence example, and I have the AOI that I created to interface with the HMI. This is something you're not going to be doing in this class. You're not going to be writing any AOIs, so don't concern yourself with that. What you should concern yourself with is the bit latch sequence. So here I have the sequence itself, and you can see that because I have a comment that says bit latch SOS sequence. Here we have the timers that the sequence uses, and here we have the sequence outputs. So all of this is grouped together because this is all, as a whole, a sequence with a couple of different pieces. The sequence itself, timers, and outputs. But then there's further structure. So we have the sequence and all its pieces, but then we have here underneath this comment every step of the sequence. So in this logical grouping, we find all of the sequence steps. Here we find all of the timers that are driven off of sequence steps. Here we find all of the outputs that are driven off of sequence steps. See, this is what I mean when I say there should be a logical and consistent grouping of rungs. So each of these is a rung, as you know, and so you can see the logical reason for why they are grouped together as they are. And when I say grouped, you can see that the groups are interrupted by rung comments. And so the rung comments are placed to describe the group. So here we have a group of rungs that are going to decide which sequence step we are on, and they're so described. Here we have the group of rungs that show, or not show, but provide our timer functionality, and that's what they're described as. And here we have our outputs for the sequence, and that's what it's described as. So this is readable in that we have good comments, and it's logically structured in that we have logical and consistent groupings. One more thing to say about it. Notice we have names of tags that also make sense. And so let's take a little closer look to be able to read these tag names. So first, in the sequence itself, we have sequenceexample.go. So this is the start signal that comes from that AOI that I made. Again, you don't have to worry about making an AOI, but I mean it's still well named in that we have sequence example, and that's exactly what it is, and there's an attribute called go, which is intended to start the sequence. Then we have the first step of the sequence, which is called step 1, show S, which makes sense, right? Because we are going to show SOS on the screen, so this step is going to show the S. The next step is called step 2, show O. So this tells the number of the step and what the step does. It's pretty good naming. Step 3, show S, because we are showing S again. But you can tell these apart because here it's step 3 and here it's step 1. So we are able to know what step number we're on and what that step does just by looking at the tag name of that step. That's powerful because now we don't have to put comments for every single rung and explain what each of these tags does. And if we did that, actually, what you would begin to do is you would have overload, and there would be so many comments you wouldn't consider any of them important, and you would ignore all of them. So too many rung comments is a bad thing. Instead, use rung comments sparingly and to help provide commentary on the order that you have and the structure that you have. For additional commenting, use tag names. We see this continued in the timer section. So here we have the logic that drives the first timer. So when step 1 is on and step 2 is not on, start this timer. And this timer is called the show S timer because it's going to time how long the S is shown. Because SOS is supposed to be it's supposed to have a specific timing to it, so that's what this is imposing. So we see the timer tags are named appropriately, and we see that we can read these steps and understand exactly what each of these does. There's a logical grouping, and we have a rung comment to describe that logical grouping. As a final example here, we have another rung grouping, which is the group of outputs for the bit latch sequence, and we have a comment to describe this group. And then we have the steps that are named appropriately to be able to give readability to each of the rungs. And we have outputs that are named appropriately so that we understand what they do. So when step 1 show S is on and step 2 show O is not on, we are going to show the S on the HMI screen. And the same with O and the same with S again. So we have exactly one more time. We have logical and consistent groupings, comments to divide those groups up, to separate those groups from each other, and to provide a description of what that group does, what the total impact of this group of rungs is. It provides the outputs for the sequence. Then we also have appropriate and helpful tag names. This is the requirement for this lab moving forward. Appropriate and helpful tag names, logical and consistent rung groupings, and rung comments to describe that rung grouping and separate it from other groups of rungs.